I Prime 95 and got for 24 hours at 4.2.
Get home from practice.
And the
sit there.
processor temperature barely went above 60.
They were to do homework, so I just do it in class before the class.
All right. Well, let's go ahead and get started. The first thing is I got good news and bad news for you guys. The good news is I have started to grade the exam, and the bad news is I'm not quite done with it.
Surprise.
I spent a little more than 2 hours on question number 1 all by itself, because first I had to write a script, write a program to generate the proper output of the traces first. Okay, because otherwise I would have to manually trace every single algorithm to find out what it is supposed to be. So I wrote a program I probably spent about 40 minutes to do that, because I forgot certain things about Perl. I had to look up how to do it. And then I spent the next hour and a half or hour and 15 minutes or so just grading it. I think there were about 39 students or less, fewer, who turned in the first exam. But looking through each one, especially the ones that do not match the expected output, just go through line by line and look for the first deviation and try to figure out why it is not the correct answer. That took a lot of time. Because it's not just matching, but it's me trying to figure out, okay, which concept or which misunderstanding or misuse or mistake is causing this program to not perform the way it is supposed to. So that's why it took much longer. I wouldn't say a little, but it took much longer than expected to grade the first question. The second question should be easier because now I have a little template for the script, so to adapt it to the second program wouldn't take that long. Yep.
So in the script that you wrote to grade it, did you write in a print for going through each?
Well, I can show you the script actually. If you guys are interested, I can show you exactly what the script looks like, and I think that's really relevant for this class too, because it's kind of what we're doing. Exactly.
Programming.
Except this one has some features that may be a little bit kind of more than what we have talked about in this class. So let me see if I can do that. Okay. I have to log into one of my machines first and then hop onto the other one because only one is exposed to the internet.
Are you logging onto your server at home?
Huh?
Are you logging onto your server at home?
I'm logging to one of my servers at home. And then I have to log into the other one, which is not exposed to the internet. There we go. Okay, so go to Documents, cisp300. And your grades are not here, so there's nothing really important here. So the funny thing is, I use Python, printq.py, is print question.python, and that's the one that I use, to kind of randomize the questions. When there are multiple versions of the same question, that's the script that I use, to randomize so that different copies of the exam can get a different question or different alternative. The Perl script is in X2, which is exam 2. And this is the program. Syntax highlighting is awful here. Okay, so this is the Perl program that I wrote to basically, it asks for the student ID, and then it just cranks out the rest of the code. Basically, it just shows me what it is supposed to look like. It's a little bit beyond what we have talked about in this class, but you can definitely identify certain things that we have talked about. Like in this case, we have a conditional statement, and this construct here is basically bar a bar, or in this case, it's bar argv bar, which means it is checking the size of an array. And then down here we have the usual thing. We have a local variable called I, and I is initialized to 0, so I can declare a local variable, and then also initialize it to the value at the same time. And these are the actual output statements. It's push. It has to do with before I print out the entire thing, I don't know how wide of a column I would need. So I cannot just print it out right away because I don't know exactly how wide of a column I would need for all of the columns. So that's why I'm storing all the output into one array first, and then I would do some post-processing, look at the entire column, and then figure out what is the widest item, so I know how many characters to allocate to each column, and then I can print it out, in a formatted way. Everything else is kind of the same thing. Array A in our class is, basically it is shown as @A in Perl script, because in Perl the symbol @ means that it is an array. Okay, so you can actually designate a particular variable as an array by using the @ sign. This is equivalent to our I is less than bar A bar. So instead of using I by itself, it has to be a $I, because in Perl variables or scalar variables are preceded with a $sign. Okay, and array variables are preceded with an @ sign. The other part, which is the scalar, FA, is bar A bar, okay, because it's converting an array into a scalar, which is basically a number, by looking at its size. So that's, the concepts are very, similar to what we talked about in this class. I think we are all familiar with this line here. X gets X times 10 plus A bracket I. But you can see that all the extra $signs, and it has to do with, in Perl, all the variables have to be preceded by a particular symbol. Now, you might want to say, but isn't A an array and it has to be preceded by an @ sign? Well, in Perl, it depends on how you want to use array A. Okay, so when you're indexing, each element in array A is actually a scalar, and that's why it is preceded by a $sign and not an @ sign. Yep.
If there's scalar variables, are there other types of variables?
Yes, there are three main types of variables in Perl. One is scalar, which is basically a number or string. The second type is an array or list. Okay, so they're basically the same thing. And the last one is what we call a hash. A hash is a map. In other words, instead of using a number for indexing, you can use a string for indexing. So it's basically a lookup kind of mechanism. Yep.
So the modern phenomenon of hash tagging.
Hash tagging.
I don't think that has anything to do with it at all.
No, it's a social media. You use
I know what it
the
is.
string variable to find information about it. And
That's basically what it
social
is.
media.
Yeah. It is related. The concept is related. Yep. So, and this is our conditional statement. If A bracket I mod 2 equals to 0, and you can see that, here, instead of using one single equal symbol, I have double equal, because single equal is assignment. Double equal is comparison, checking for equality. And the mod operator that we call MOD in this class is %, which is consistent with C and C++ too. So for the most part, the syntax of Perl is borrowed from C and C++. Okay, but C and C++ does not use the $sign in front of each variable name. So this is the main part of the algorithm. So your algorithm, or the part that you have to trace, is essentially everything from here all the way up to the end of the loop. All the push instructions or the push statements are only there to generate the output that I can see, so that I can cross-check your submission with the expected output of the program. So that's only the easy part. That's the easy part of the of my program. The more difficult part of my program is to go through here. Now this is something that we have not talked about in this class, because it is also missing in C and C++. The for each thing is a handy way to basically say, okay, for this particular array, for each iteration, I just want to look at one element. Okay, so I don't really need an index to control which one I'm looking at. It is automatically going from the first to the last. Okay, so it's a very handy feature when I really do not care about the actual index of each element. I just want to say, for each element in this array, I want to do this kind of processing. So this part basically is just figuring out how wide a column has to be, because otherwise I will be printing things in a varying column thing. It will be hard for me to visually check and say, oh, this is the value of I, and this is the value of X, and this is the condition, and so on. So this makes sure that everything is nicely formatted. And then once I know the width or the length, but the width of each column, I actually go ahead and print everything. So this is the last part of the program, which prints out all the columns on a row-by-row basis. So it looks at each output, and then it formats it so that I have all the items per column. The whole thing is written in in Perl. And the way it is run is just q1.pl, and then I give it a particular student ID, and it generates the output with nicely formatted columns, so it all lines up and stuff like that. So that's what I spent the first part of my grading session on, is the tool itself, and then I use this output, match it up to whatever is turned in. And then the really lengthy part is to figure out, why is this not the same as that? As you said, it took me longer because I did not want to just say wrong, no points, right? So I want to figure out exactly why is it wrong. Is it because of array indexing issues? Or is it because that person did not understand loops or conditional statements or the mod operator? So I try to break it up into smaller portions, so that if someone has a problem with one particular aspect of an algorithm, that person would not lose all the points.
Did you create any subroutines for this program right here?
No, this program has no subroutines. I just wrote the whole thing as one big algorithm.
You're going to use it though for the other questions?
Yes. So this will serve as quote unquote a template for all the other questions. Except the other ones would also have array items and elements, because some of the other algorithms would change the array elements, so I would have to display those too, just so that I can see how the array elements are supposed to be changed during the process. Yep. Any questions about this particular script? It was a lot of fun. I actually enjoy writing scripts like this. That's what I like to do. The actual grading part is a little bit mundane, but it has to be done.
You like to solve the problem, not actually do the problem.
I like to make a tool to solve problems. Yep.
I was wondering why you had us write out our student IDs for each element of the array instead of just having a single element set.
Like a fixed set for all the questions.
Instead of having a fixed element set, you just decided to have us write down our student IDs so you wouldn't get bored, right?
So you wouldn't do it.
So you wouldn't get bored while you were grading our assignments.
So you know who was who while you're grading it and all that?
Well, that's one.
It
And
prevents
two,
cheating.
Yep. Well, so that copying from somebody else would not make any sense in this case, so people won't even try it. Yep. But now the script is published, people can actually try to put it into a flow and go like, oh, okay, I can do this in my next exam. Except it involves a lot of massive editing to this script to make it work with another exam question. And people who can do it don't need to do it.
They're not taking the exams.
Otherwise, it's just for the challenge of it, right? It's like, okay, I can do this and I take it as a challenge.
Happy look at a white hat sort of board.
Right. That's one reason of hacking, is just to see as a challenge and say, okay, if the RIAA thinks they don't want people to copy music and they think this will protect their content, I just want to break it, just as a challenge. I don't care about the actual music content afterwards. Yep.
Sort of like the caption people did. They had broken the code of the captions, the words that sort of pop up in a screen picture.
Right.
They just did that just because.
That part is actually, I think it's an open standard, or is it encrypted?
I'm not sure.
CAPTCHA?
Yeah, the caption. Oh, the capture or caption?
CAPTCHA. The security
Capture?
thing.
Oh, that thing, I
Proprietary.
think you talked about it a
It's
little bit, and
proprietary.
how it is, it's actual scanned results from actual documents.
Right, so the original CAPTCHAs were, the code was broken, so they were still getting spam bots. So what they did is they took actual pictures of writings in books, because CAPTCHA was originally a solution for the Gutenberg project, which is scanning all old text into digitized format. And a lot of the old texts are handwritten. So what they did to improve CAPTCHA was they included pictures of actual words that were handwritten. So it's one thing that the computer knows, because the computer can decode a pixelated text, but it can't decode a picture text. So it's one thing that the computer knows and one thing that the computer doesn't know. And you have to answer both. You have to put an answer into the second. But the computer doesn't know the answer. It just accepts that answer.
You mentioned it's kind of like crowdsourcing for
Right.
for parsing and interpreting things that the computer cannot understand. Because you can actually have people to quote unquote vote on it.
Mhm.
You ask it to 2,000 people, and if 1,800 people decided this is actually saying DEFI, and then you can say, okay, this bitmap is representing DEFI with some confidence, because 1,800 people say that. Yep. So that's kind of interesting. That's an interesting concept, using crowdsourcing and forcing people to participate because they need that to sign up for accounts and whatnot. All right. So any questions before we kind of continue to talk about records and types? No questions? All right. All right. So maybe we'll start with a sample program today. Because all the sample programs are here to kind of illustrate these concepts. And what we'll do is we'll have a sample program that is kind of presented in stages. So we'll first present it in the initialization part of this stage. First of all, we'll define a record, and we'll just call it "and" because otherwise it will take a lot of typing. In the record "and" we have several members. The first member is v, which is an integer, and then the second one is next, which is also an integer, and this is the definition of a record "and" for node. Okay, uppercase N, it actually stands for node, N-O-D-E, node. Are there any questions about this? Now, N, uppercase N, in this case, is the name of a template. Okay, in other words, it's a cookie cutter. Okay, at this point, we don't have any cookies. We just have a cookie cutter, a user-defined type at this point. And then what we'll do, it will have record. I'll just call it nodes. Okay, record nodes is going to look kind of interesting because the first thing it has is, and they'll give it a name. I call it pool. Okay, and pool itself is an array of. We'll just make it short. 5 nodes. Okay, 5 ands. So in this case, each element of pool, which is a member of nodes, is of type uppercase N of a node. Okay. And we'll go ahead and have another member called first, which is an integer, and record. So now we have 2 different types, user-defined types, and they are related because the second one refers to the first one. Before we go any further, we just want to see, okay, but what does it look like? Okay, if I have one single item that has the type of nodes, what does it look like in the inside? So we'll first take a look at that. And the way to do it is to define sub, and we'll just call this main. This is the first program, in this series. And inside we have one single local variable, which I will call this. We'll just give it a name of x. Okay, so it's kind of generic. And this is nodes. And we'll define, and the definition of the subroutine right away. So this subroutine doesn't do anything at all, except to allow me to illustrate what it looks like. Okay, what is the layout of the local variable x in this case? And let me make sure that I save this file. Call it nodes 1 because there will be other ones too. All right. We don't need comments because there's nothing printed, and there are no conditional statements, and there are no global variables. That makes the precondition really easy to specify. And then we start execution on line 12. The first line, the only line that is outside of the definition of a subroutine. And the return line number is post. Pretty standard stuff. Then we have to allocate for the local variable x. Okay. So the first thing we notice about x is it is of type nodes. Okay, so because it's of type nodes, we look up the record type nodes. And record type nodes has two individual, well, I wouldn't say individual, but it has two members. The first member is pool, which by itself is an array. But each element of that array is a record n. So what we have here is x has pool as one component. But inside pool is an array. So pool itself has elements, index 0, 1, 2, 3, and 4. And you can see that I'm allocating two columns for each because each element of pool of x is of record n. So within n, which is here, we have one member called v, one member called next, v, next, v, next, v, next, v, next. And it really makes sense to shrink these columns, at least one. So we can see it more clearly like this. And if I want to use the merging of the cells to really represent what is one particular element, this is the way I would do it. And then pool itself will be all of these columns. Are we doing okay so far? Now x is not just that. Okay, x has one more column associated with it because it also has a member called first. So x has an extra member called first, which itself takes up one column. And this, everything from column C to column M, collectively, that's my array. That's my local variable x. Are we doing okay so far in terms of understanding how big the local variable x is and how it breaks up into smaller parts? It has one member called x, which itself is an array, and each element of pool, is a node, is record n, and within that we have member v and member next. And in this particular program, we are not doing anything. So as a local variable, everything starts with an unknown value. So plus we do it. And then we start execution on line 11, which is the end of the subroutine. And obviously, this is not going to be a very exciting. Oh, I forgot one thing. I didn't forget it, but it's in the wrong column. So line 11 is the end of the entire subroutine. It has got two things to do. One is to look up the return line number. We're supposed to get to post. And then the second thing it has to do is to deallocate all the columns that we have allocated, which are all the columns basically, except for column A, and indicate that we are done with this. These columns are now deallocated. And that's the trace of this particular program. Doesn't do anything at all. Doesn't do anything useful or exciting except to allocate for the local variable and then immediately deallocate it. But it does help us understand how local variable x is actually organized. Okay? Because x itself is a record, has two members. But the first member is not a very simple member because it is an array. Even each element of that array by itself is a record which has two members. But you can see that we can nest things like this, any way we want. I mean, we can have an array of records. We can have a record that has a member that is an array, and and we can just keep stacking things, on top of this. Yep.
For line 1 there, record n, what else can we call that?
Say again?
What else can we call that in C++? Is that like a descriptor or a template?
You mean on line 1
Yeah.
1 to line 4?
Line 1 to line
It's a struct in C.
A struct, okay.
Yeah, in strict C, it is called a struct, but in C++, you can call it a class. A class is basically a super duper structure that gives you more options in terms of visibility, and you can also include methods and other things. But they're basically the same thing. It's a way to define, basically a cookie cutter. So basically, a class and a struct and a record in this class, they're essentially the same thing, but the name class implies that it is used in an object-oriented programming context instead of a kind of more traditional procedural programming context.
5 through 8 is the same thing? 5 through 8 is the same thing?
5 to 8, is defining another struct or class.
Right. Okay.
If you want to be specific, a struct is a class where all the members are public. Okay, which doesn't make any sense in this class because we really have not talked about what a class is and what object-oriented program is, but those two are closely related. All right, so this is our first program. I'm not gonna mess around with this program anymore, but instead we'll save it as a different name, and then we'll start with nodes 2 and see what we can do with this particular program. And before it's still going, that's good. All right, so this is the second program. The first thing I want to do is to change the definitions of the subroutine a little bit. So in this case, I'll define sub initialize. Okay. And initialize as a subroutine is going to require a by reference parameter. And the by reference parameter is, I'll just call that y. It is of record type nodes. So it's going to take in the reference to a nodes type variable, and it'll go through the initialization here. We have a local variable I. I starts with 0, while I is less than bar y dot pool minus 1. Do the following. And we say y dot pool bracket I dot next gets I plus 1. I get I plus 1. And while, and then we have one last item here, y dot pool dot I dot next gets -1. So fix the indentations first. And then we can have our usual main subroutine on line 18. Define submain. Local x is nodes. Invoke initialize. And then we use our local variable x to specify parameter y, which is passed by reference. And that's all we are going to do in main. And define sub. And we have invoke main as the last item. And just fix a few things here. We'll be ready to trace it. All right. So this is our new program. Okay, has one extra subroutine called initialize, and we'll go ahead and see what it is going to do. This is a combination of several concepts. It has a concept of records. It has a concept of passing by reference. It has the concept of array indexing, and it's mixing up all these things. So we want to figure out how all of these things can combine, and how do we trace it? How does this program work out in this case? To shrink it a little bit just so that we can display all of the lines on the screen at the same time, all of the columns. On this side we have a trace. We'll go ahead and erase everything here. delete all content, including formatting. And this time we do have comments, so column A is going to be used for that. And then we have line number. The precondition has nothing to say because we do not have any global variables. And we start execution on line 23. It is invoking main. Main needs a return line number. And it also needs to allocate for x, which is our local variable. The return line number is post. Nothing too exciting about that. X has post. Post has 5 elements: 0, 1, 2, 3, 4. And then X also has one extra field called first. Each element in, that's supposed to be pool. P-O-O-L. Okay, so in pool, each element is a type N, so it has a V as a next, V next, and this one is not supposed to be first. First has to go to the next one. There we go. So we have first. So pool, okay, each element will take up 2 columns. And then pool itself is the entire array, so it will take up 10 columns. X will take up 11 columns because it is made out of pool, which has 10 columns, plus first, which is 1 single column. So this is the layout of memory after we initialize, after we allocate for local variable x. There we go. Are there any questions at this point about how we do the allocation? It's basically the same as last time. Okay, this part really has not changed from last time, except they're off by 1 column compared to last time because we have comments taking up column A. And as any local variable, once again, we have to say that, okay, they all start with an unknown value. So we have to put question marks on every single column to basically say we have no idea what is the initial value of each item or of each column when we get into the subroutine. The subroutine main starts on line 21. Line 21 is invoking initialize, passing x by reference to parameter y. Are we still doing okay so far with this code here? Okay. It is a little bit complicated, seems to be kind of overly complicated, but it's one of those things where it actually has a purpose, has a reason why it is like this. We'll go ahead and split the screen, so this way I can work with different parts at the same time. Okay, on line 21, we are invoking the subroutine called initialize. Initialize does not return a value, so return line number is fine in this case. When we come back from initialize, we have to go back to line 22, so the return line number is line 22. It has 1 parameter and 1 local variable. The parameter is called y, it is passed by reference, and then the local variable is I, and as a local variable, it starts with an unknown value. Y is passed by reference, so if I go back and look at x is going from column D to column N, so the reference or the pass by reference parameter is going to be the reference of the same columns. So in this case, it's column D to column N, just like that. And so that's basically what we have at this point. Let me see if I can show the entire screen. Yep, we can. That's good. Are there any questions at this point? We are ready. We are almost about to execute the first statement inside initialize at this point. No questions? All right, so now that we are in the subroutine, we will continue execution on the first line of initialize, which is line 12. Line 12 doesn't do a whole lot. It just initializes variable I to 0. And on line 13, we evaluate the condition. In this case, is I is less than y dot pool bar y dot pool bar minus 1. What is bar y dot pool bar? Should it be 10 because it uses up 10 columns, or should it be 5 because it has 5 elements?
5 elements.
We have 5 elements, exactly. So when you use the bar notation, we are not counting columns. We're counting the number of elements. In this case, it has 5 elements. So we are basically comparing I, which is 0 at this point, to 5 minus 1, which is 4. 0 is less than 4 is true. Then we move on to the next line, which is on line 14. This is a little challenging because I don't have enough screen space to show both. We can shrink this a little bit more, so we can scroll this off the screen just a little bit.
So just to make sure, y dot pool is basically saying like a bracket I, basically. Like so, y dot pool.
Y dot pool is the
bracket I
same as
is
x
a.
dot pool, basically.
Okay.
Yep.
No, I'm saying like so the y dot pool part in the array, like bracket I. Is
Right,
the same
because
as
it's an
saying
array.
A bracket I. Okay.
Right, because it is an array.
Okay.
Or it refers to an array in this case
Inside of
because
it.
it's passed by reference.
It's an array inside of a variable.
It's an array inside a record type. Yep. So the way we get to it is a little bit more cumbersome this time because y itself, or what y refers to, is not an array, but the first member pool is an array. So that's why we have to refer to it as y dot pool instead of just pool, because pool by itself is not a variable, it's not a parameter, but y is. Are we still doing okay so far at this point?
You could shrink the other algorithm down a little bit and probably give you more
It's true.
That is true.
There we go. All right, so now that we're on line 14, this is kind of the really nasty one because, well, as an assignment statement, we always do it in a certain way. We always evaluate the right-hand side, which is just I plus 1. I, well, it's off the screen again, so we have to scroll it to show it again. I has a value of 0. So 0 plus 1 on line 14 is just 1. The question is, where am I storing that 1? Well, we have to track this kind of big mess down one step at a time. First, we have y. Y is column P, but y itself doesn't do anything. Y is only an alias of something else. Y is an alias of column D to column N. So we're talking about column D to column N here. But we don't really need the entire Y. We just need a component of Y. The dot, the period symbol is basically apostrophe S. So we want to access the first part of the record, which we call pool. But pool itself is an array, and that's why we see the bracket I operator or the indexing operator here. I has a value of 0, so we're indexing to the first element of the array. But each element of the array is not just a number, it is also a record on its own. So we are now designating just one part of the element that we are accessing. In this case, we're accessing the element or the member called next. So it is column E that we are modifying to a value of 1 on line 14 in this case. Yep.
Now, could we go y dot pool gets I plus 1, and then so everything will get I plus 1?
Yep.
Is that not?
Because it would.
Why not? Not within this program, but just could you?
None
write
of the
it?
programming language that I know of, has a way to apply the same operation automatically to the same member of all the array elements inside the array.
Okay, and so then you can as well go y dot pool I gets I plus 1, because then that would be y.
Because it has
pool.
two things.
Yeah,
You have to designate which one gets I plus 1.
It can't make that a
No.
connected time.
No, because if you leave it up to the compiler to make it up, it's ambiguous. Do you want to change both V and next, or do you just want to change one of them?
Well, that's what I wasn't sure if certain compilers made that.
No,
connection.
none of the programming languages that I know of, can infer what we want to do and do it in a simpler way. So this is basically the way it has to be done, if that is the effective thing that we want. There was another hand. There was another question. Okay. All right. So that's what line 14 does. Line 15 does something a lot easier. It's just adding 1 to I. So I goes from 0 to 1. Then we go back to the beginning of the loop, which is on line 13. The same condition is still true. So I'm just going to copy and paste it. So this time, without actually tracking everything down, on line 14, I can tell you right away that it is this column that is updated to 2. Is everybody convinced, or do you want me to track it down? Let's track it down one more time. Just one more time, we'll track it down. Okay. So we are now talking about line 14. This is the instruction. It's an assignment statement. We first figure out what is the right-hand side, which is I plus 1. I now has a value of 1. I plus 1 is 2. So the right-hand side of line 14 is just basically 2. The question is, which column are we updating? We start with y, which is a passed by reference parameter. We look at y. It is also known as column D to column N. Here is column D to column N. Column D to column N is of record type nodes, okay, which is fine. You have to make sure that X and Y are of the same type, because you cannot pass by reference, something to a different type. But in this case, it's okay because X, which is a local variable, is of type nodes. Y, which is a pass by reference parameter, is also of type nodes. So that's okay. That's good. Y has 2 components, or now in this case, it's referring to column D to column N. Has 2 components. It has one member called pool and another member called first. We are, according to line 14, we are only interested in the first member, which is called pool. But pool itself is an array, so we have to do an indexing operator next of bracket I. I has a value of 1, so bracket 1 is now referring to just column F and column G. Column F and column G by itself is also a record. I cannot store a number into an entire record. I have to designate which part do I want to store it into. And that's what the dot next is for, because within these 2 columns, I'm using next to designate a particular member of the record. And that's why column G is the one that is updated to a value of 2. Are we doing okay so far with this code up to this point? So the rest of the algorithm is fairly simple, because we are just basically repeating lines 13, 14, 15, which updates the value of I to increment it by 1. Go back to line 13. This condition is still true. Go to line 14. We're going to update the next of the 3rd element. So in this case, this one we get a 3. Then we get to line 15. We increment the value of I by 1. I'm having problem lining up everything now. It's the wrong line?
No, you're fine.
Now it's the right line. Okay. So this is line 15. We go back to line 13 again. 3 is less than 4, so the condition is still true for the last time. Then we go back to line 14. This time it is column K that gets updated. So this is now 4. Then we go to line 15. We add 1 to I, and that's aligned. So now I gets a value of 4. We go back to line 13. The condition that we have been checking is now finally false, because 4 is less than 4 is false, and now we get out of the loop. After we get out of the loop, we have to continue execution on line 17. And line 17 is going to do something that is kind of strange, because it's putting a -1 into the y.pull bracket I.next. Does it still make any sense? Is I still a valid index into the array? What is the current value of I at this point? 4. I has a value of 4. And is 4 still a valid index into that array called pool? Yeah, pool has 5 members, so the last member, or the last member has last element has a index of 4. So now we're updating column M with a value of -1, like that. And then we get to the end of the subroutine. I think I will leave the rest of this program untraced, because it's really just cleaning up everything. So is that okay so far? up to this point.
Where did you get, you lost when you got the negative one. Where did you get the negative one from?
The negative one is coming from line 17, the right-hand side, right there. What it is, this is what we call a linked list, okay? Because one way you can look at this is we have 5 nodes, okay? So each node, you can look at it as a single item. So we have 5 of these things. And they're all elements within the same array. And if you look at how I initialize the member called next, it's kind of like having the effect of this one, of this. The first element in the array is having one of its member as an index of the second element. And then the second element has the next member, quote unquote, pointing to the third element. This one points here, this one points here. But the last one has a negative one here, which is not a valid index into any array, because arrays can only start indexing from 0. So what we are doing here is basically saying, oh, by the way, this is the end, this is the last one. This is one way to draw, to represent that this is not pointing to anywhere that is reasonable, because it is the last one. It's an indicator we are at the end. So that's logically what is being represented here. This is called a linked list. You won't see this concept again until you get to, I think, cisp300, as in data structure class. But we can do something similar using arrays and not using pointers. Are we doing okay so far at this point? Yeah, just initializing, not really knowing what to do with these nodes. Yep.
Say pointers or using arrays instead of pointers?
Well, using the index, okay, we can kind of emulate the effect of a pointer, because what it is I want to know where I'm supposed to go after this one. So having next as an integer to store the index of the next node of the same array, we are now achieving the same result as using a pointer, because I can now find the next node.
That makes me think of memory allocation.
Except in this case, there's no memory allocation, because everything is statically, well, not statically, but it is pre-allocated. I only have 5 of these things. I cannot have more or less. Are there any questions about this? Now, if there are no questions about this, I just kind of want to talk about something without any code, but I want to talk about it because I want you to understand why we have to define nodes like this and have the concept called a pointer to point to something else. Okay, so that one node can find one or more of the other nodes. Okay, so we'll go ahead. I'm keeping this one up on the board, but at the same time, I'm going to use a different color to draw a different picture. Okay. How do you sort numbers? If I give you a sequence of numbers that is out of order, how do you sort it so that it becomes sorted or in order again? There are several algorithms. Okay, there's insertion sort, which is the easiest way, but it's also very time-consuming. Insertion sort is kind of like this, okay, and I have to do it to the exam, because I want to sort everything, so it's easier to grade. So I can just move from one item to the next instead of having to do random access in the gradebook. Insertion sort is kind of like this. Whatever list I have is already sorted. So when I add one new item to the entire list, I will flip through the entire list that is already sorted to find the right place to insert the new item. But that algorithm is actually kind of slow. It has a time complexity of big O of n squared, or bar A bar squared. Do you still remember? Oh, this one is out.
Careful, don't be permanent.
Right. Well, the permanent one is not exactly permanent, but erasing it is kind of embarrassing, because you have to overwrite it with an actual dry marker, and then the solvent of the actual dry marker will dissolve the ink of the permanent marker, and therefore you can actually quote unquote erase it. But it's a lot of trouble. Okay. So we talked about the big O notation, or in this case, let's not use n, because we have been consistently using bar A bar as the number of elements. Insertion sort has a complexity of this. In other words, if you double the size of an array, insertion sort will require 4 times as much time to finish the entire algorithm. If you triple the size of an array, it will take 9 times as long to finish the algorithm. So it's not really that efficient. It's not the best. The best sorting algorithm has a time complexity of bar a bar times the log of bar a bar itself, which is a lot better. Okay, because when bar a bar becomes a huge number, this is basically becoming just bar a bar, because the log of bar a bar increases very slowly as bar a bar becomes a huge number. Okay, so this is the fastest sorting algorithm we can find. Okay, I'm going to erase this because it's not relevant in this case. So I'll just give you an example. Okay, we'll have a sequence of numbers that is out of order. 4, 3, 10, 1, 2, 5, 6. Again, and then we have 11. Okay. So in this case, let's just say that we can represent the same number twice in this organization. The way it's done, this is called a binary search tree. Okay, which is related to binary search, but not exactly the same thing, because we're constructing something here instead of looking up something in an array. The way it works is the first number is by itself. Okay, 6 is the first number, it is by itself. And then what we do is we have a convention. 6, each thing is called what we call a node. It has a left-hand side and a right-hand side. Everything to its left-hand side are less than or equal to 6 in this case. Everything to its right-hand side is larger than 6. Okay, so that's a rule. 6 is the first item, so it doesn't belong to the left or the right-hand side of something else because it is the first item. What about 3? Which side do you think 3 should go? The left-hand side, less than or equal to. Okay, so 3 goes here, and we just draw a little line here to say that, 3 is on the left-hand side of 6 because it is less than or equal to 6. And then we have the next number, which is 10, and we always start with the first number, which is 6. Where should I put 10 when the first number is 6? The right-hand side, right? Because 10 is greater than 6. So we got 10 over here. And then we got 1. Okay, so how do I find a place to put 1? Well, each node can only have 2 sides. So I cannot have another thing hanging out of 6 on this on your left-hand side. So what we do is we say, okay, let's compare 1 to 6. 1 is supposed to go to the left-hand side of 6. Fine. We go to the left-hand side of 6, and we say, well, but somebody's there already. Then where should I put that 1? On the left-hand side of 3. So we put the 1 here, like that. What about 2? Well, we start from the beginning. So 2 is less than 6 is supposed to go to the left-hand side of 6. Somebody's there already. 2 is less than 3, so it's supposed to go to here. But somebody's there already. But compared to 1, where should I put 2? On its right-hand side. So now we have 2 here. Now we have 5. 5 is less than 6, it's supposed to go here. 5 is greater than 3, it's supposed to go here. Great, nobody is there yet. I'll be the first one. 5 is going to be hanging off here. And then we have 6 again. So in this case, because I said that we can have duplicate values, so we still have to, we cannot say that 6 is here already. We say 6 is less than or equal to 6, so it goes to this side. Somebody's taking that spot already. 6 is greater than 3, it's supposed to go here. Somebody's taking that spot already. 6 is greater than 5. Nobody's taking that spot. And I'm going to end 6 here, the second 6. And then we have 11. 11 is greater than 6. It's supposed to go here. Somebody's taking that spot already, but nobody's taking this spot because 11 is greater than 10. So it hangs on to the right-hand side of 10. This is what we call a binary search tree. Okay, BST, as in short. Yep.
Well, if we were to have 6 again.
Sorry?
What would happen if we had a 6 again, because it can't go on the left or right of
let's try to figure out. Let's put a 6 one more time here. So 6 is less than or equal to 6. 6 is greater than 3. 6 is greater than 5. 6 is less than or equal to 6.
Or equal to.
Yep. So that's how it's going to place itself. Okay, this is a binary search tree. It's kind of nice because I can very quickly figure out whether something is in there or not. Okay, let's pick a number and see how long it takes to figure out whether that number is there or not. Let's pick 7. Okay, 7 is not one of these numbers, but let's try to see how we can find out that 7 is not one of these numbers. 7 compared to 6, 7 is greater. So if 7 was here, it would be on this side, right? 7 is less than 10. If 7 was here, it would be here, but there's nothing there. So right now, I can conclude that 7 is not anywhere within this BST, binary search tree. What about something that is there? Well, we actually did it quite a few times already. What about I want to find 5 again? Okay, search for 5. 5 is less than 6, so if 5 is in the tree, it will be on this side. Well, this is not 5, but that's okay, because if 5 is in the tree, it will be on the right-hand side of 3. We just got 5. With the conclusion, 5 is in the tree. So you can see it is kind of like binary search, because for each step, you only have 2 choices. Do I go to the left-hand side, or do I go to the right-hand side? And you make a conclusion when you find the value that you're searching for, or you get to a place where, oh, there's nothing there. Nothing is there yet. Okay, then you make the conclusion that the value that you're looking for is not in the BST, it's not in the binary search. Yep.
And this way, could we find out how many recurrences a specific number has? Like say 6, could we find out?
To find all the occurrences of 6 depends on the structure, because you can see the 6s are not consecutive. They're not right next to each other. So it depends on between the 6s what other values are inserted into the tree. So it's not very easy to find out where all the consecutive numbers are in this particular representation. Yep.
Does this take up more memory than some other
Representations?
Yes.
This one takes up a little bit more because when you look at each node, how would you represent each node? That's related to exactly what we were talking about. Okay. So in this case, I'm going to use the projector again to represent each node. I'm not going to actually do anything because to trace something like this would take a long time. Okay, we can at this point we have enough concepts and material to write an algorithm like this. Okay, except to trace it, it's going to be very time consuming. So I'm not going to waste the time to do it, but we can kind of talk about how do we define each one. So we have BST node as a record type. In other words, how do we represent one single item in the tree? There are 3 things that we have to remember, and therefore there are 3 members. Yep.
So it's either equal to, less than or equal to, or greater than or equal to?
It's less than or equal to or greater than.
Yeah.
That's it.
Always.
Yep, just 2. Okay, so each node has 3 things to remember. One is the value itself. In other words, the value of the first node is 6. The value of the node to the left of the first node is 3, and so on. So that's basically what V, or the member V, is for. It's just representing the value. And then we have 2 extra ones. One is called left. In this case, in this class, because we don't have pointers, left is going to be an integer, which is the index of the node to the left. And then there's another one to the right, which is also an integer. It's just a way to find the other node. So that's essentially how we represent a binary search tree using, or a node in a binary search tree using a record. Yep.
We do the same things using 2 variables, but instead of having left be integer, you make it a boolean, make it a true false statement. And so if it's left, it's true, then it's on the left. If it's false, then it'll be automatically assumed on the right.
But I need to know where to find that node. I'm not interested in whether something is there. I need to know where it is. So an integer is basically left and right are integers. Once we have everything here, they will be initialized, or they will have the index of the element that it is linked to on the left or on the right. Okay. Are there any questions about this? Now this has a lot to do with recursion as well. Okay, if you look at this as a binary search tree, what is the property of a binary search tree? Well, if you look at any binary search tree, okay, we have a node. Okay, the node can potentially have two sides, the left-hand side and the right-hand side. Whatever we put here, doesn't matter whether it's empty or it's full, you know, it has 20 gazillion items. Everything here are less than or equal to this value. On this side, it's the same thing. Everything that is here, it can be empty, there can be nothing, or it maybe have a gazillion items, but everything on this side are greater than the value that we have. This is a binary search tree, okay? And then you look at one item here. What do you think this looks like as this whole thing itself?
The same thing.
The same thing. It is all by itself a binary search tree. Because when you look at the node on the right-hand side or the left-hand side of a particular node, that node by itself is what we call the root of another binary search tree.
If you separate it from the original, it's still its own tree.
Exactly. Yeah, it has the same structure. It follows exactly the same rules.
So the question is, how do you represent that?
How do I represent?
Because, I mean, these records would store themselves into an array, correct?
Right.
Okay, and so how would you represent that in an array? Because
Aha.
you would start with one container.
That's a good question.
You would start with the one index of the original number that
Right.
is in the middle of all of them.
Right.
And then it would index to left
Okay.
or right values, correct?
Okay, we can do something like this. What I'll do is I will do is, let me see how I'm going to do it. This is going to be a little bit messy because we have 3 items per node, and then we have a bunch of nodes. So I'm going to have to figure out how to represent this. Okay, I'm going to have to convert it from this orientation to turn it 90 degrees, just so that it shows more reasonably. Okay, so let's say T is a tree. Okay, so T is a tree. We have the first element here. Each element has V, left, and right. So I'm just turning everything 90 degrees. Is that okay so far? Okay. So these 3 rows now represent the same element, like so, and each element has these items. So what I'll do is I'm going to replicate this like 4 times. So we have an array of 5 elements. And without showing you how to initialize everything, we'll just go ahead and say, this is our 6. Okay, the first thing that we see is 6, and then the second thing that we see. Okay, I need to fix these 2. Index these. Okay, there we go. So let's say we follow the same order as what we see on the board. So the next number is a 3. So the next number is 3, but 3 is to the left of the 6. So the index of the node containing the 3 is going to be the left of the 6. Is that okay?
That's what that means, right? Like true or something? That's like saying true for the left, the value 1.
No, it is 1. It is really saying the left node of the one that is containing 6 is the node of index 1. Okay. And then the next number is 10. And 10 is greater than 6, so the 10 will go here. And because it is to the right of the node that is containing 6, and we store the index of the node containing the 10 as the right member of the node containing the 6. And then the next number is 1. So then we traverse the tree. Okay, so we look at this one, 6 versus 1. 1 is less than it. We go to the left-hand side. The left-hand side is here. It has a value of 3. So we have to go to the left again, but there's nothing there yet. So now I can allocate this one to represent a value of 1, and then the left of the node containing the value 3 will be the index of the node containing the 1.
3.
Oh, is that 3? Okay, there we go. And then the last number, which is the 5th one, is a 2. So now we have to traverse the whole thing again. Start with 6. 2 is less than 6, we have to go to the left. 2 is less than 3, we have to go to the left. 2 is greater than 1, we have to go to the right. Nothing is there yet, and we do have one node available, so let's take it to represent the value of 2. Now the rest, they all have to be negative ones, because we have to represent the fact that these particular ones do not have the left-hand side or just the right-hand side. So these are all basically negative ones. And that's how we can represent a binary search tree using the concept of a structure or record plus the concept of an array. Yep.
But how do we know that left and right refer to an index? Does that make sense? Yes. How do we know that left and right refer to an index inside the actual array?
It is by implication. So the programmer basically has to keep in mind what is the left member of a node and what is the right member of a node.
So like, for instance, in the program, it would be like T bracket 0 dot, or yeah, T dot, I don't know, T bracket 0 dot left would get.
Can be a valid index
Gets
when
T
it is
bracket
not
1 B.
when it's not a valid index, when it has a negative one, that means that whole side does not exist yet. Okay? Is that okay so far? The representation itself? Okay. Now, how do I print everything in order when I have a binary search tree? Just think about it. Okay, just think about it from the high level. Okay, from the perspective of one single node. Okay, so somebody is invoking this subroutine to print everything. Okay, and this is the node that you're supposed to process right now. Yep.
You have to go to the leftmost column, go to the next one on the right, and the next one right of that.
Okay, I think you got the right idea. Okay, so the idea is if I am one particular node in the binary search tree, then from my perspective, to print everything in the right order is like this. I'll print everything on my left-hand side first because they're all guaranteed to be less than or equal to me. Okay, so I'll print everything there first. Everything on my right-hand side are greater than me, so maybe I should print myself first. So that order is just, I'll print everything to my left-hand side, myself, and then everything to my right-hand side. Okay? So let's look at the first subproblem. Okay, the first subproblem is, okay, let's print everything to my left-hand side. What do you think is the left-hand side itself, the entire thing? It's just like you, right? The node on your left-hand side is just like a node as you. So that node will have to state exactly the same thing. I'm going to print everything to my left-hand side, then myself, then everything to my right-hand side. When everything is printed, I go back up to whoever was telling me to print something, and I'll let that person or that node to handle the rest. Yep.
So would you actually start from the greatest number?
Sorry?
You would actually end up starting from the greatest number because you print.
No, you start with the least number because it's on the left-hand side.
Right, but the last number would be the one that tells everything.
Let's try to figure out how it's going to be printed in this case, okay? So when you start, you're always started with what we call the root of the tree, which is the top part of the tree. It's kind of interesting because it's like looking at the tree, but it's upside down. The root is up and the leaves are down, okay? And that's exactly, those are the terms, anything that does not have anything under that is called a leaf, okay? And then the first item is called a root, so it's an upside down tree, actually. Okay, so this is the first guy, right? But this guy says, I'm not ready to print myself because I want to print everything to my left-hand side first, okay? So the red pen is just indicating, when it gets control, and then I'll use a black pen to actually indicate, when it is printed. So now we are here, okay? We are now at the node of 3. The node of 3, when it first gets control, it's saying the same thing, okay? I'm not ready to print my own value until I'm done printing everything to my left-hand side, and then myself, and then everything to my right-hand side, okay? So this guy says, okay, I'm not ready to print anything. Let's defer that to the node on my left-hand side. And then this node containing the value of 1 is going to say exactly the same thing, except it has nothing to its left-hand side. So right away it says, I'm done printing everything to my left-hand side because there's nothing to my left-hand side. So now it prints its own value because the order is to print everything to your left-hand side, then yourself, and then everything to your right-hand side. So 1 is going to be the first number to be printed. In other words, if I use the black pen to indicate the order of printing, this is the first one. Now that I've printed myself, what do I do as a single node? Print everything to my right-hand side. Okay, so I'm gonna say, hey, 2, go print your stuff. 2 says, okay, I'm gonna follow exactly the same procedure. I'll print everything to my left-hand side first. But guess what? 2 has nothing on its left-hand side. So it's automatically done. Then it goes back to 2 itself and says, okay, it's time to print myself because I'm done printing everything to my left-hand side. So now 2 prints. Okay. So it prints a value of 2. And then it will print everything to its right-hand side. But once again, there's nothing to its right-hand side. So now 2 is completely done, and that subroutine invocation returns, right? Where does it return to? To this guy. And that guy says, okay, I have printed everything to my left-hand side. I have printed myself. I have printed everything to my right-hand side. I got nothing to do now. I'm returning back to this guy. Okay, so now we're back to the node that contains the value 3. But this guy just got back from its left-hand side. What is the next thing it has to do? Print itself first. So now this is the third one to print something, and it's printing a value of 3. Then what do you think it should do? Print everything to its right-hand side. Okay, so it will tell this node and say, okay, go print everything. Okay, so it will tell to the node that contains the value 5 to do exactly the same thing. The node containing 5 will say, I'm going to print everything to my left-hand side. But I don't have anything to my left-hand side, so that's done. Then I will print myself. So this is, in terms of the ordering, this is the 4th item to print, and it will print its own value. And then it will say, okay, now that I have printed myself, I'll print everything that is larger than my own value, which is all the things to my right-hand side. So it will tell, oh, you're on my right-hand side, go ahead and do your thing. This guy will say, okay, I'm going to print myself, but only after I print everything to my left-hand side, which is this guy here. So if you look at the actual order of printing, this is the 5th item to print, which prints a value of 6. This is the 6th item to print, which has a value of 6 itself. Then we'll try to print everything to its right-hand side, but there's nothing there. So it goes back to this guy, and then this guy said, okay, we're all done. Then we go back to this guy. Now we're back to here. So this value is going to be the 7th item to print, which prints a value of 6 again. And then it's ready to print everything to its own right-hand side. So we'll tell this guy 10 to print everything. 10 will say, I will print everything to my left-hand side, but there's nothing to its left-hand side. So it's automatically done. And then it would be time to print itself before it prints everything to its right-hand side. This is the 8th item to print. So print 10. And then it will be ready to tell this guy to print everything. That part is easy because it has nothing to its left-hand side. Go back to itself. This is the 9th item to print something. So 11 will be the last item to print. We will try to print everything to its right-hand side. There's nothing there. And then we go back to this one. It's all done. We go back to this one. It's all done. And that's how it will print everything in the right order. Okay. How am I going to write an algorithm like that? Do you think it's going to be a complicated algorithm?
It's just recursion.
Yep, it's going to be recursion. And it is surprisingly simple when you look at it from the recursive perspective. I'll go ahead and write the algorithm, but you don't have to worry. I'm not going to ask anything like that in the final exam. I'm not going to give you a problem like that. Here's a binary search tree or some data structure that you have never encountered before, and I say, write an algorithm to print everything in order. But I think it's exposure. Okay, this is exposure. Whether you can recall this by the time you get to CISP 430 is a whole different question.
Well, that's what the YouTube videos are for.
Exactly, and you can download it, put it onto your own DVD, and
Yeah, the YouTube video of the whiteboard.
put it into a nitrogen purge. They'll save, so it's not going to be oxidized in any way. Second?
No.
He made a good point. The YouTube video of the whiteboard.
Okay.
A lot of stuff was on the whiteboard today.
He's working.
A lot of stuff was on the whiteboard today and wasn't caught by the YouTube.
That's true. This is why I just bought myself an Elmo.
Did you order it?
I ordered that, but I'm not sure when it's going to arrive. Elmo, E-L-M-O. Not that Elmo. It's what we call a document camera. So it looks like a lamp, about yay high, and it has a camera. And what you do is you put something under it, and it's just a camera. And I have the tool to basically project what the camera sees on the screen. Sorry?
The new classrooms that they just built over there have that.
Say again?
The new classrooms they built.
The new classrooms?
Over by the science buildings, they have that.
Yeah, well, these classrooms were built in the 50s.
Looks like a digital projector.
Yeah.
Yep, that's basically what it is. But it's USB based, so I can actually overlay the projection on screen, here, and if the whole thing is screen recorded, so will that.
Right.
Yep.
You just basically use a webcam on a stand.
That's what it is. What it
Yep.
is.
Yep. It's basically a webcam on a stand, but this one has it has a resolution of 5 megapixel. But I think the lens itself can be, not saying that this one has the specialized type of lens, but when you look at camera lenses, the actual focal plane of the camera lens may not be plano. It may not be a two-dimensional flat plane. A lot of times it's curved. But in this case, if they do it right, they should have used a specialized camera lens where the projection itself or the focal plane is flat. So that way you start with a flat object to begin with, but the projection into the camera's CCD or CMOS array will also be flat. So everything is going to be in focus at the same time. Cheaper cameras have a curved focal plane, so we can never have everything in focus at the same time. We have one portion of the surface in focus at any particular time. So that's why it may be specialized, because a webcam is used for conversation and just talking for the most part.
It's not the background.
Exactly, the background does not matter, and your face is not flat to begin with, unless you're one of those characters in Minecraft, right? And then you have a flat face, and therefore a plano focal plane is going to be helpful in that case. But don't turn, because as soon as you turn, then it's not flat anymore. Then you need what we call a swivel, tilt and swivel lens, where the lens itself can do this. That's for architecture purposes. But these days with Photoshop, people no longer spend that kind of money on a camera lens. They just use Photoshop, go like, oh, make the correction, done. All right, well, we are running out of time, so I'm gonna write the algorithm maybe next time. But the algorithm itself is surprisingly easy because we're looking from the perspective of a single node. Print everything to my left-hand side, invoking the same subroutine. Print myself, print everything to my right-hand side, and I'm done. So the only complicated part is to say, is there anything to my right-hand side? Is there anything to my left-hand side? But we can tell easily, because when left or right is -1, that means there's nothing to that side, and therefore we can stop the recursion. Okay, so we'll focus on this next on Thursday, and if you guys want to do it ahead of me, go ahead and give it a try, and then we'll talk about it on Thursday.
It's funny. I had a question when you first started doing the node, like what does V mean and what does next mean, and then you like did it, and I'm like, oh, now I get it.
What if it's something like while?
There's no while.
There isn't.
It's just this if, because you need to see whether it is time to stop or not. Okay, this is what it is.
Because
If I wanna do it
because it'll keep
shorthand,
going. It'll keep going down.
Yeah.
Basically.
So basically, if n is a node, okay, this is like super shorthand. So basically what it is if n dot left, right, exists, then you say vst n dot left. And then print myself, okay, so you say print n dot v, which is my own value, and then you say the same thing, if n dot right, if I have something to my right hand side, this is vst n dot right, recursive call, and if, that's it. So logically speaking, this is what needs to be done, except in implementation, we say if n dot left is not -1, do this.
Because it'll keep going down the tree.
Exactly.
Yeah.
It is recursion.
So you would represent that as greater than or equal to 0.
Right. Yeah. Basically, exists means greater than or equal to 0. Exactly.
But then, like,
But the concept is just that. I mean,
so
just
it would
checking
say,
whether this-
so this would be T though, because the array unit was T. So it'd be T dot. Whatever.
No, it's going to be T bracket something because we use
And this is the shorthand. You're
indexing.
just representing.
This is
that with
like a
shorthand.
way shorthand.
Yeah.
Yeah, you're gonna go into this in more detail next time.
Yes, absolutely.
Are we
That's why I'm
actually going-
saving this file so that next time we'll start with the initialized, array, and then we'll just write the algorithm to do the traversal. It's called traversing a tree when you're visiting all the nodes. It's called traversing.
One
it.
more thing, I really like the switched
Orientation.
Yes, that's much more convenient. Like, why weren't you using that
Right,
the whole
right.
time?
Yeah, but it's not easy when you need to trace like how it changes over time.
You're trying to call it a tree, but you're doing it
Right.
vertical or horizontally or something.
Well, you're doing it upside down to begin with.
Wow. We only need 2 comparisons, huh? Right? Is that
Yeah, 2
There's the
comparisons.
statement-
One here
statements.
and one here
Because it'll keep recurring until it gets to the end.
until there's nothing.
Yeah.
Well, you can also stop here if you want to put a big conditional statement up here that basically says, if the index is -1, there's nothing to do, and then just go back right away.
So this would be like a condition. So it'd be like if
Yeah, yeah.
BSTN equals or
No, if n doesn't exist or does exist, do this, then you can erase this and that. And then you say else, do nothing, go home. because I do not exist. There's nothing to do. So that would actually be more concise too, because you only need 1 comparison instead of 2. But in terms of the trace of the recursion, it will be deeper because you're 1 level deeper than otherwise, because you're terminating when you are nothing instead of terminating when you have no left-hand side or right-hand side.
I got a question for you that's totally not related to the class.
Okay. Do you guys have any questions?
Thank you.
No? Okay.
So
Yep.
4.2
4.2?
Jelly Bean.
Oh, okay.
Do you know if they changed Samba, the version of Samba that it uses for sharing? Because it has a
Samba
version.
has 4.0.
Well, it does have a version of SMB that it uses
Okay.
whenever you're here. I'll show you this. Probably can't access it from